All right, so welcome back to the second lecture of parallel computing or parallel programming. So today we are going to have a short refresher on essential parts of C and C++ that you are going to need for doing your homework assignments and your project and learning how to do parallel computing in this class. So just to be mentioned in the beginning, I'm not going to teach you C and C++ from scratch. I just review some important concepts in C and C++. So you should be able to study this by yourself. If you want, you can find a lot of good resources in this website, cppreference.com. You can see a screenshot up in the left corner of this slide. And if you want to study using books, this book is quite good and modern. It's 21st century C. So you can also start reading that book. Okay, so C and C++, there are two programming languages. There are compiled language, which means that your source code is compiled into machine instructions using a compiler, and then those machine instructions are being executed on your hardware architecture. So both C and C++ syntax, which are a little bit different, are used in parallel computing, but in different contexts. So for example, when you write GPU programming code using CUDA for NVIDIA GPUs, your syntax is somewhat similar to C. But if you write other kind of parallel programming code, like multi-threaded code, you probably will use C++ syntax using C++ standard library called thread library, right? Both C and C++ require manual memory management, which we're going to talk a little bit about today. But memory management is more important if you write your code in C, because modern C++ has has some functionalities for automatic memory management, but when you write your code in C, you should be really careful about how you use memory. And in C++, you have direct support for object-oriented programming, or OOP, but in this course, we really don't care about OOP too much. But if you want to write numerical software, you should use OOP for your interface design and for code reusability. And there are some features from C++ that we are going to use, which are exception handling in C++, which is missing in C. We use a standard vector library in C++, a standard thread, smart pointers, and some others. Okay. So this is basically what from C++ we are going to cover in this class, and you need to know. All right, there are some common issues and common bugs when you write low-level code in C and C++, which I listed them here. But I would like to ask you about each one, and someone should give me answer, as we discussed in the previous lecture, that I'm going to ask a lot of questions during the class, right? So the first issue that you might get when you write C and C++ code, essentially low-level code, is seg faults or segmentation faults. So can anyone explain it for me? So what is a segmentation fault?
Can you hear me?
What?
Yeah, so segmentation fault, I think I will give an example when we, let's say, initiate an array in the RAM, but not in the heap, and it's bigger than what is allowed, so we enter another segment.
Yeah.
So the OS will reply with the segmentation fault.
Yeah, so that was very important, that the OS is responsible to give you the segmentation fault. So essentially, when you want to access memory that is not available, or it belongs to another program or something similar, or some similar situations, you will get the segmentation false. So very good. So what about memory leaks? What is a memory leak in a low-level programming language?
When we don't free memory, it will keep accumulating, and after time, it will overflow some segments, I think, in the
Well,
RAM.
memory leaks refer to the allocated memory. So you requested the operating system to allocate some memory for
Yeah.
your program, but you didn't free up that memory. So then you are leaking memory. So you have to make sure that after every memory allocation, you free up that memory. Okay, so now another student, please. What is use after free problem that we have in C++ code?
It's when we free a memory and we mistakenly can use that memory while it doesn't exist anymore.
Yes, that's correct. What about double free?
I have no idea about that.
Well, double free, anybody else? No?
It's probably freeing two times.
Yes. So it means that you freed your memory once and then you, by accident or by mistake, you freed your memory again. So this is called double freezing. All right. So this is basically these bugs are related to memory. These bugs are very important and you will get them when you write your code in C++, especially if you are a beginner. So make sure that you follow best practices of memory management that we will discuss today to avoid these things. And it is up to the programmer to solve these memory problems. All right, but there are also some other bugs in low-level code, like in C++, that is also in other programming languages. And these bugs that I highlighted them with the red color are related to multi-threaded programs or program with multi-threads, right? So the first one is race condition, and the second one is deadlocks. So what is a race condition in a multi-threaded program? Can anyone tell me that? It should be covered in operating system class that you might had before.
More than one process trying to access the same resource.
Can you repeat,
At
please?
the same time, more than one process try to manipulate one resource
Yes, some
simultaneously.
data. Yes. So this is called race condition when you have multiple threads, but they are working or writing essentially on a same data. So uh, they can manipulate their own data and they can destroy things. What about the deadlocks? What is a deadlock in a multi-threaded program?
I think it is when two threads get locked waiting for each other, so
Yeah,
they wait forever.
so that's true. So deadlocks are bugs that you can get in your multi-threaded programs when you have different threads and they are waiting for each other. So and this waiting can be forever. So this is called deadlocks. And then you can have integer overflows and some other low-level problems. All right. So these are the bugs that these are the bugs that you should be aware of, because when you write your code, you should detect these bugs and you should avoid them. And these things are very difficult to detect in many cases. So this takes experience and practice. So make sure that you have like that you practice a lot writing low-level code. But anyway. All right, so to be able to write C and C++, you probably know about them already, but I just wanted to mention here for the beginners, you'll need some tools. The first and the most important one that you need to install on your computer is a compiler. So you need a compiler on Mac, and on Linux, you can use GCC compiler. On Mac, you can install a GCC compiler using Homebrew, which is a package manager in Mac. So using this brew, install GCC. So let me see if I can highlight it here. So using this brew, install GCC, you can install GCC on Mac, which is a C and C++ compiler. For Linux machines, you can use this sudo apt install build essential, which which is a package that contains C and C++ compiler. On Windows, things are a little bit tricky. You should install MSVC, Microsoft Visual Studio Compiler, which comes with this Visual Studio IDE from Microsoft, or you can install this MinGW, which is not really recommended, or you can install WSL on your Windows 10 or Windows 11. WSL stands for Windows Subsystem for Linux, which installs a Linux distribution, typically Ubuntu, on your Windows. So it's kind of a very thin virtual machine on your Windows, right? Then using this WSL, you can install the C++ compiler on the Linux distribution on your Windows, right? And so this is about the compiler. Then you need to have some IDEs for your development. So you can have this Visual Studio only on Windows nowadays, so it's not available on Mac anymore. And for multi-platform IDEs, you can use this Visual Studio Code, which is available for Linux, Windows, and Mac. You can use this CLion, which is a JetBrains IDE. I think with your student email, you can have the non-commercial but fully functional version. And there's also another relatively new one, which is called Cursor, which is similar to Visual Studio with GitHub Copilot. So this one also is good, but I personally recommend you to use this Visual Studio Code or CLion. Or if you are on Windows, you can also use this CLion, which is quite a complete IDE. But you are free to choose like anyone that you want. Okay. All right. So, by the way, to install this WSL on your Windows machine, you can visit this link to activate Windows Subsystem for Linux, and also install Ubuntu on your machine. Anyone here in the class knows about this WSL2 and have any experience working with that?
Yeah, in Windows, I had to use that for installing Docker.
Okay. So yeah, so now you can install Ubuntu if you want to, and then there is also another extension in Visual Studio Code called WSL, if I'm not mistaken. And then you can have your Visual Studio Code on your Windows, and then you can use Linux terminal using that. I don't have my Windows machine here with myself, but I would I wanted to show you, but it's not here. So okay. Any questions about the compiler and IDEs? All right, so it seems that it's clear for everybody. All right, so now we can start the actual lecture, which is about C and C++ syntax. So the first program that you should be able to write in any programming language that you want to learn is the Hello World program. And with the Hello World program, essentially, if it works, if the Hello World program works, it means that the whole thing, like in the language, is working, like about the tools, compilation, and everything. So essentially, if you want to write a C program, you need to create a file with this .c extension, right? So let me raise it here. So with this .c extension, and then you can write your program in that C file. So for example, in our case, we are just including something called a header file, which we are going to talk about, which is a standard IO header from C library, from C. And then every C program should start with this main function. So you have this int main and void in this case. And then within these curly braces, you have your program, right? So let me erase things here. So this should be quite familiar. And this printf is a function provided by the C standard library here that you can use for writing strings on the standard output, okay? And then you need to compile your program. So in this case, we use this GCC compiler, and then you specify the name of the C file. And with this flag -o, you can generate your executable. In this case, we name it hello, okay? I will show you a demo in a second, but before that, let's see how we can do the same thing in C++. In C++, your file extension is CPP or CXX, but we use CPP. And for printing a string to the screen, you just need to include this IOStream library provided by C++. Similar to C, you have this main function in C++, and you use this syntax to write on your screen. So basically, you have to use this std or a standard namespace in your C++ library, which is available in this IO stream. And then you use this cout followed by this symbol, and then you can write your string, right? So it's kind of similar. And then instead of GCC, you use on Mac and Linux G++, which is a C++ compiler, and then you specify the name of your C++ file and also the name of the executable, right? But the name of executable is not really mandatory, so you can also compile your code like this, okay? And it will create an executable with a default name with a.out that you can execute. I will show it to you in a demo. So let me stop sharing at the moment and open my VS Code. Okay. Okay, can you see my my window here?
Yeah.
Okay. Just let me just remove it from here so it's better now. Okay, you still see my window, right? Because I removed something. Yes?
Yes.
Okay. All right, so here, this is my VS Code. So in the in the left side, I have two folders, C and C++. So in the C folder, I created a hello.c file, and here you can see the program that I showed you. So you need to first include this stdio header file, right? And then write your program. All right, so let's see how we can compile this. So here I use my GCC compiler because it's a C program. And then I have this hello.c, but let me first check out to the library and to the folder. Okay, so GCC hello.c. And if you just execute that, in this folder, you will get a file called a.out, and then you can just run this file, right? So it prints this hello parallel word to your screen, right? Okay. But if you want to have your own executable name, you can use this -o flag with any name that you want. So if you run that, you see that you will get a hello executable here, right? And then you can also execute that. So very easy, right? And you can do the same thing with C++ file. So, okay. but instead of GCC, you use this G++. Hello.cpp-o hello. Okay. And here in this folder, you will get this hello file, which is a binary file, that is your executable, and then you can execute that. Okay. Very simple. All right, so let's get back to the slides. Okay. So now I have a question for you. If I add this -- save temps within as a compiler flag here after like this GCC or after hello.c, what happens? What will I get in this case? Because that's very important flag for you to check your code from a low-level perspective. So anyone knows?
I think it saved some file somewhere in the directory, right?
What?
Never mind. Maybe I remembered wrongly.
Well, okay. Any other ideas? What does it do?
Does it save some low-level codes before translating it to an executable?
Exactly, yes. So when you run this compilation command with this -- save temps, it also gives you the assembly code that it generated for you, and also some other intermediate code that the compiler generates during the compilation process. And this is very important because especially in parallel computing, you want to know how your code is performing from assembly point of view. So that's how you can get the assembly version of your code. So let me show it to you that what files will be generated in this case. So let me share my IDE again. All right, so here, for example, let me just remove this hello. Okay. So here, I write this -- save temps, and then I recompile. And here, not it generate, I mean, apart from the executable that it generated for me, so it also generates a lot of other files. So this hello.bc, hello.cpp is my own thing, my own program. I have this hello.ii, which is the same file basically after including the header file, right? And what is important for me is this hello.s, which is the assembly file, the assembly version of my program. So you can see here the assembly code that the compiler generated for my hardware architecture. And also this hello.o, which is the object file. So the binary version, the machine instruction format of this assembly file. So the assembly file is a text file that you can read, but hello.o is called object file, which is the machine instruction version or the binary version of this assembly code. Okay. All right, so when you write your program and it doesn't work as expected, and you want to check how it is really being executed on your CPU or your GPU, you can use this save temp flag in your GCC compiler. By the way, it doesn't work on GPU exactly like that, but you can on CPU you can use these save temps to get your assembly code version of your program. Okay. And it doesn't matter if you're using C or C++. It works for both GCC and G++ compiler. All right. So let's get back to the slides again. Okay, so how you can compile, how the if you have multiple files, multiple source files, like multiple CPP files, what the compiler does is the following. So it first generates this object file based on each file, based on each source file, right? And then there is a program called linker that links all of these objects files and creates an executable program for it. And if you want to see the content of this object file, if you want to deassemble the object file and we want to see the assembly code, you can use this object dump utility that comes on Unix-based operating system like Mac and Linux, right? Okay, so I don't show it here, but you can try it by yourself. All right, so the next concept in C, which is the actual syntax, is preprocessor. So the preprocessors are some directives that you can write within your C program, and it allows the compiler to replace them with their actual definitions, and they have different applications in your C program. The preprocessor directives are usually started with this hash sign in your C program. And now I can show you some applications. So for example, with this hash sign and then define, you can define a constant value, especially in your C programs. In C++, you don't really need to use this for defining constant values because it has its own const data type, the const keyword. But for C, you should define constant values like that. So you define, for example, in this case, pi, and followed by its value. And when the compiler wants to compile your code, the preprocessor part of the compiler will replace pi by this 3.14 number, right? Similarly, you can define constant functions like macros. So for example, here you can define a square and within this parenthesis x, and then you can define the definition of this function within this parenthesis. So again, whenever the compiler sees this square thing, it will replace it by this definition. All right. So here I showed you how you can define constant values and functions. Another application of preprocessor is to have this conditional header inclusion. So for example, here you check if you don't have this config.h header, you define it, and then you can have the header content here. So this will make sure that you don't include the header file twice in your C source code. The next one, which is important, is this pragma preprocessor, which provides a compiler specific instructions. So when the compiler sees this pragma thing, and then it reads the word after, it can make some decisions. So for example, in this case, the compiler ensures that the header file that contains this pragma once is included only once, right? But this pragma can come with other instructions that you will learn in this class, mostly when we are working with OpenMP. So using this pragma, we can parallelize our program quite efficiently using OpenMP. And another preprocessor is this include keyword followed by this hash sign, which is used to include header files, our functions and classes and variable definitions and declarations in our C program, similar to what we included for printf for standard input and output, right? Okay. And then you can define, there are some idioms now that I can show you. So for example, you can define a debug preprocessor here, and then based on that debug, you can change the compilation flow. So if the debug micro was defined, then you want to print something, otherwise you don't want to do that. And then it's up to the compiler to include this printf in your program or not. So you can also check your code with that, or you can have different version of your code. So you can define a version micro, and then based on the value of the version, you can include different part of your code in your program. Okay. So for example, another application of this is to write platform dependent code. So for example, here you can define a platform. It can be Mac, Windows, or Linux, and based on that, you can write different platform dependent code depending on the operating system that that you're using. So preprocessors are quite important, and you should be aware of that. Most of the time, you're working with this include thing here and also here for for having this conditional inclusion. And when it comes to parallel computing, you use this pragma thing a lot. So keep these three in mind. All right. So C++ supports some primitive and non-primitive data types, including integers, floats, and doubles. So now I have a question, and someone should answer me. So what is a primitive data type, and what is its difference with a non-primitive data type? So can someone explain that to me?
Primitive is like the basic one. It's like directly related to the memory characteristics, like float will relate directly to a register, let's say.
Yeah.
The other one, there's like more complex.
Yeah, the primitive data type, that your definition is correct. For non-primitive data types, they are basically the combination of primitive data types. So this is, you can also see them in that way as well. So first, in this code snippet, you see the different integers that C++ and C support. So you have int keyword, which allocates 4 bytes on your memory. You have short, which allocates 2 bytes. So it has a smaller range compared to int. You should be aware of these things. And then you can have long, which has 4 or 8 bytes, depending on the system, and long, which is the very large range that you can have. Then you can also print them out. So you can read this printf things, how to print each one on the screen. Okay. And then you can have this unsigned int, which is only used for positive numbers. Okay. And here you can see the similar thing for the floats. So here you have a float data type, which stores 4 bytes, single precision. And then you can have the double, which stores 8 bytes on the memory and with double precision. So anyone can tell me what is the difference between the single precision and double precision for these floats and double?
The precision of the number that is represented.
Yes, because the floating points and the floating point numbers are kind of difficult to represent on hardware, because they can be unlimited, but the hardware is limited, so you can have different precision. In this case, the float data type has single precision and double has double precision. So basically, this stores, I think, 32 bits, and this stores number in 64 bits. Okay. When you work with CPUs, you usually use this double, but for GPUs and GPU computing, you should use single precision, right? Okay. So this is about the integers, floats, and doubles. And in C++, not in C, you have another data type, primitive data type called bool, which is used to store Boolean. So it's a true or false. All right, so let's see about non-primitive data types. The first one that we are going to talk about is strings. Strings are an array of characters in C. So for example, you can define a string in C like that, and then you can perform operations on your screen, on your string using some predefined and built-in functions in C. This is not recommended anymore, so we really don't use C-style strings. That's why I didn't explain it in detail. But in C++, you have a new, not a new, but in C++, you have this a string header that you need to include. And then you have this standard std string data type for having your strings, right? So for example, here our string is greeting, and then you can just store your string. So it's similar to Python, for example. And then you can perform operations on your screen and on your strings, and then you can print them to the screen, right? So we prefer to use this std string from C++ over this C style string. All right, another non-primitive data type is arrays and also vectors. So an array, which is introduced in C, is a fixed size collection of similar data items that are stored in a contiguous memory locations. So this is the actual definition of arrays in C. So there are some important things in this definition. So the first thing is that an array is fixed size. So you have to know the size of the array in the compile time. So the compiler needs to know the size of your array, and then the compiler will allocate it for you using the operating system calls. And an array consists of similar data items. So you can have an array of integers or an array of floats or an array of doubles, but you cannot have an array of integers and floats and doubles all together, right? And they are stored in contiguous memory locations. So that's quite simple to understand. So for example, here you have an array, right? These are the array indices that you can have here that are mapped into memory locations. And here there are array elements, 2, 4, 8, 12, 16, and 18, okay? So let's see how you can define an array in C. You should know about arrays in CL style, because when it comes to GPU computing, to write GPU programs, you usually use CS style arrays. So that's why you need to know them. So you can define them in different ways, as you can see here. So for example, here we are declaring an array of integers with 5 elements, but it is uninitialized. So it is not a good practice. Usually try to initialize arrays at least with 0. So here we have an array of integers with 5 integers, but we initialize them with 0. And here you have an array. You didn't specify the size, but the size can be inferred from the right-hand side. So we have 3 elements, okay? And here in this program, we just created an array with 3 elements, and those elements are integers, and then we looped through all elements and just print each element to the screen, okay? So this is how you can declare and define an array in C. So as I mentioned, the size must be known in compile time, and you cannot change it on the runtime. So there are some issues with these C-style arrays. So they don't have built-in functions for resizing, inserting, or deleting. So everything should be written by the programmer. They are typically not safe because there is no built-in bound checking. So if you want to access an element in an array beyond the number of the elements in the array, so you won't get an error in many cases, but you might get a segmentation fault. But the language does not check the bounds. Arrays are quite fast because there is a minimal overhead, because they're very simple. And the most important thing about arrays is that they need manual memory management. So the programmer is responsible for managing the memory that the arrays use, okay? So, but in C++, you get a new type of array, which is called vectors, right? So for using vectors, you should include it, the vector header file, and then you use this std vector thing as data type. So this is called this, that's too many things here. Let's give it a second. All right. So here, for example, I just allocated a vector of integers that you can write this like that. And these braces are called in C++ templates. Okay, so you should study a little bit about templates if you want to work with vectors in C++. And then you can also, so here we just declared an empty vector of integer. In the second version, we defined a vector of integers with 5 elements, and each one is initialized to 0. And here, which is introduced in C++ 11, you just declare a vector of integers, and then you can initialize it with some values, okay? And it's important to know the difference between C++ vectors and C arrays. So C++ vectors, they support dynamic size, the dynamic allocation. So their size can be changed during the runtime. This is not true for C arrays. And they have a rich interface to work with. So you can have this pushback, popback, pushback for inserting element, popback for removing an element, empty for removing all elements, and you can get the capacity and size. So it means that you have some built-in functionalities in C++ that allows you to work with vectors easier compared to C arrays. So vectors are typically safe compared to C arrays because there is a built-in bound checking on vectors. So you can have this, if you use this .at function or .at method in each vector, so you get an error if you want to access an element beyond the size of the vector, right? And it's also compatible with most of C++ standard library algorithms, and it also provides automatic memory management. So when you work with vectors, you don't really need to worry about managing your memory so much, okay? All right. So the next data type, which is available in both C and C++, are pointers. Pointers are essentially variables that hold the memory address of another variable, and that another variable can be anything. So pointers, they store addresses of other things in C and C++. So for example, here you have an integer x equals 5. So 5 is stored in this this variable. And then you can define a pointer to that variable. So now somebody tells me, what does this ampersand x mean in this context? What does it get?
Referring to the address of this variable.
Yes, it gets the address of x in the virtual memory, and then using this syntax, which is int star, you are just here declaring that p is a pointer with this star to an integer, and its value is the address of this x, right? So p is a pointer to an integer, and its address is and its value is the address of this variable that you get by this ampersand, okay? So pointers are very important when you write low-level code on CPU or on GPUs. So try to have some practice with that. So try to solve some problems with that. I try to include it in homework assignment 1. So here, for example, we have an array of 3 integers, 10, 20, and 30. And here we have this pointer has the address of the first element of this array, right? So somebody tells me why we don't have ampersand here behind this number. Why I didn't write int star p equals ampersand numbers.
The name
Because
of the
yeah,
go ahead.
no, you go.
So what's that? Arya, can you tell me that?
It's because the array name is already a pointer.
Well, they are not exactly pointers. The arrays are not exactly pointers, but they are treated as pointers. So yes, if you have an array, the first, and if you only use the array name, it means that you're having a pointer to the first element. So the numbers in this case, which is this, is the address of the first element, and then you can have it stored in this pointer, right? And then you can, if you want to have its value, you have to dereference the pointer. So here, if you have the star before the pointer, when you are not declaring it, and when you want to use it, it gives you the value stored in that pointer, not the address, right? So for example, in this case, we are just adding 1 to the pointer, which means that we are referring to the next memory location, and then we want to get its value. So it's kind of similar to this notation in C. So it needs some practices if you are completely unaware of these syntax in C++, in C and C++. Okay. But in C++, apart from raw pointers, these are called raw pointers, you have something called smart pointers, which is available in, I think, C++ 11 and beyond. So you can, with the smart pointers, you don't need to be worried about memory management. So they have automatic memory management, and you can have different smart pointers called unique pointers and shared pointers. You can study them by themselves, by yourself if you want to. But unique pointers can only point to one data type, but shared pointers can point to different data types, different values in the memory. And this is how you define them in C++. So for example, here, you need to first include this memory header, and then you define a unique pointer. And this is a pointer to an integer that you can write, and that you can define with this template notation. Then it follows with the pointer name. And then you should use this make unique if you want to create a unique pointer, or make shared if you want to create a shared pointer. And then you specify the integer, data type, and the value. Okay. So this is how you can define a smart pointers. But in this class, we don't use them so much, but it's important that you aware of these smart pointers because of some memory management that you might need in the future. Okay. So one of the important topics when you write C and C++ code is how to manage memory and how memory actually works in a C program. So here in the right, you can see the memory model that is used in C and C++, and each memory, and it is divided into different memory locations called a stack, heap, BSS data, and text segments in your memory of a process of an application. So I would like to ask someone, ask as a volunteer, to explain these different memory segments of a C application for me. So do you have any volunteer?
Yeah, I can try.
Okay.
Yeah, so basically, whenever we have a function, its local variables or like local data will be in the stack. The heap, basically, when we explicitly allocate things to be saved in the heap, as we see, like the stack will shrink, will extend towards the heap, and the heap will, it will expand towards the heap, and the heap will expand towards the stack.
Mm-hmm.
We have some global and static variables that are shared between all the threads or functions will be in data. The text, yeah, the executable code that is saved before I think compilation. Um, yeah, and yeah, as it explained, like BSS is like global and static variables basically,
Yes.
but the ones without initialization, yeah.
Yes, that's true. So, so you have essentially 5 data segments: a stack, heap, BSS, data, and text. So the text segment contains the executable code in the machine instructions after the compilation. The data part has the initialized global and static variables, so that you install in your program. BSS have them like this, has initialized version, so we really don't care about these 3 segments. So, but it's important to know, but we don't use them. But the most important ones are stack and heap. So let's see what are they. Well, first thing first, the stack memory is responsible for storing local variables, function call frames, and return addresses that you have. So as a programmer, you usually involve with this local variables. So if you have a function and you define a local variable inside that function, those local variables are likely stored on the stack, or depending on the compiler, they can also stored as registered on your CPUs, but they can also be stored on a stack. So there are some important things about the stack. So the first thing is the stack is managed by the operating system or by the compiler. So you as a programmer don't have control on memory on a stack, right? So as I mentioned, the stack is used to store local variables and function calls. So stacks, and another important thing is stacks are scope-based. So if you are out of your function scope, your stack will be for that function will be deleted. So and you lose a lot of you use every local variable that you stored in your function scope. It has a fixed and a smaller size compared to the heap. And who determines the stack size is the operating system. So the operating system that determines how much byte, or how many kilobytes should be the size of the stack. And it's usually a small, so you cannot really store a lot of data on the stack. Because it's a small, it's also fast. And so and well, if you want to, well, let me ask you like a question. So on Unix-based machines, what does this command do for you? So it is related to the stack memory actually, but what does it do? Anyone work with this ulimit -a command on Unix? Well, perhaps we can try it ourselves. So if you open your terminal, okay, can you see my terminal window?
Yes.
Okay, so if you execute this command, ulimit -a, you can see some numbers. And these are basically limits of your processes based on the operating system. So in that you can find something called stack size in kilobytes, right? You can also get it by this ulimit -s. So which means the stack size of my computer with my operating system is about 8,000 kilobytes, which is not a lot, right? So if you want to know the size of your stack, you should use this ulimit command. All right, so let's get back to the slides. All right, so this command gives one of the outputs of this command is the stack size. But what about heap memory? So in contrast to the stack, that is managed by the operating system or the compiler. The heap memory is managed explicitly by the programmers. So you are responsible to manage the heap memory. It provides dynamic allocation on runtime. So based on some situation on your code, you can allocate and deallocate memory on heap on runtime. And stacks were scope-based, but heap memory is not a scope-based. So you are responsible for deleting or deallocating memory after you allocated that. It is much larger than a stack, so it is used for large data structures. So if you want to store large data structures or large arrays or large data, you should use the heap memory, but it is relative to a stack, it is smaller than the stack. Okay. All right, so it is very important for low-level programmers that be able to manage the heap memory. So how we can actually allocate memory on the heap is our next topic. But before that, as I mentioned, managing heap memory is very important, but it becomes even more important if you are working with GPUs and if you want to write GPU code, because in that case you are not only you need to manage systems memory and GPU memory. So these are different things. And then you have to manage the data transfer between GPU and the systems memory. So we will talk about them later in the GPU computing lecture, but it's important for you to know before that. Okay, so let's see how we can have this memory management in C. So first we talk about this dynamic memory allocation in C. For that, C provides different built-in functions. The first one is malloc, or the next one is calloc, realloc, and free. So they have different functionalities. So malloc allocates a block of memory of a specified size on the memory, but it does not initialize that block. Calloc allocates memory, but it initialize the memory to 0. Realloc is used for resizing an allocated memory, and free is used to free previously allocated memory. Okay, so for example, here in this C code, we are allocating. Come on, this is. Let me erase this first. So here, give me a second. So here we are allocating a memory block for an array of 5 integers. So with this size of int, I get the size of an integer, and I want 5 of this size. So in this case, it would be 20 bytes because each integer is 4 bytes in the memory. So we have 5 times 4, 20 bytes. And then we use this malloc to have these memory allocations, right? And finally, we have to cast it into a pointer to an integer. And we call this pointer to an integer, in this case, air. I hope it is clear. So I explain it again. So this air is a pointer to an integer, right? And which is the first element of this allocated memory. And this allocated memory, and this memory allocation is done by this malloc function, okay? After the memory allocation request, as a best practice, always check if the allocation is done successfully. So if this allocation returns a null, it means that your memory allocation is failed. So you have to always check if the memory allocation is done successfully, and then you can return proper errors. Okay. So always check if the allocation was successful. Never do the allocation without checking afterwards, okay? And then you can use your memory that you allocated. So here we just used it, and then we print it. some values. And finally, the most important part is to free the allocated memory. So these two steps are very important. You allocate your memory, you use your memory that you allocated, but you have to free it after that. So for each malloc in C, you need to have a free after that. Never forget to free your allocated memory, otherwise you will have a lot of memory leaks, especially if you use them in a for loop or something like that. So ensure that every allocated block is later freed to avoid memory leak, okay? Each malloc must have a free after the usage is done. Okay, so in C++, things are a little bit different. So you don't have malloc, calloc, and realloc and free, but instead you have this new and delete keyword. So new is used to allocate the memory block, and delete is used to free that. So for example, here we allocated memory for an integer, right, whose value is 42. And then we use a pointer to store that memory location. If you can see here, we don't have this casting that we had here. So the casting that we done here is not needed in C++, okay? But you need to know the C syntax because of CUDA programming and GPU programming. And then you can delete the memory that you allocated in C++ like that. And then you use this delete keyword to delete that memory. So in C++, for each new keyword, you need to have a delete. In C, for any malloc or calloc or realloc, you need to have a free. So here you don't need to have a free, you have a delete. And so this was only for one integer with initialization, but here we allocated an array of 5 integers on the heap memory, right? So new, we want to allocate an array of integer with 5 elements. And here we just use this array pointer to store the first memory location of this allocated memory. And when we have done working with that, like here, we just need to deallocate or free that memory. If you are using arrays, you should use this delete followed by this brackets. But if you use just if you allocate memory for a single value, you don't need to have these brackets here. But if you use arrays, you should use this here, okay? So I hope it is clear. So there are some best practices for this memory management in both C and C++. The first one is consistent allocation, deallocation. So try to match each malloc with free or each new with delete. So I mentioned that a couple of times. Try to have error checking. So after memory allocation, make sure that the allocation was successful, and otherwise you have to send to the user of that program some meaningful errors. So the second thing is to have this error checking. And then you should check the ownership. So make sure that you clearly define which part of your program allocates what part of the memory. So this is also important. So that's why you usually want to have this memory allocation function-based or class-based. And as another good practice, when your memory is freed, so after you freed your memory, the pointer that you used to store the first element of that memory should be set to null in C or null PTR in C++, okay? And in the worst case, there is a tool called Valgrind that is used to detect memory leaks. So I think it's available on C Lion, the IDE, but I think you have to install it separately. But it is a good tool to detect memory problems. Okay, so keep these 5 best practices in mind when you are working with memory. Okay. Okay, so in this slide and the next one, I provide 2 simple examples of memory leaks So how simple you can get into this problem if you are not careful. So for example, in this code, we allocated uh, we allocated 10 integers, the memory for an array of 10 integers, right? I stored it in this pointer. We checked if the allocation was successful. We used this memory location, but we forgot to free up the memory. So this can lead to a memory leak. In this very simple case, because after this main function returns, the operating system, they deallocate the memory for the whole process, it's not a big problem. But if you do not free up your memory that you allocated in a function, and that function is in a for loop, your system will run out of memory very fast. So try to deallocate memory after you use your memory, and then set its pointer to null in C or null PTR in C++. So what's happened here? We have a repeated leak. So as I mentioned, so we have a for loop in which we have a function called leak memory in this case. So here we allocated memory for an array of characters with 50 elements. We checked everything, right? And then we forgot to fill up that memory. So then because this function is in the loop, so you are just wasting your memory and your system might run out of memory. Okay. There are a lot of corner cases with these memory leaks. So try to search for them on your own and to know what are the common bugs and what are the common memory leak problems in a typical C program. Okay. All right. In C++, actually, you have a modern, you have an idiom called resource acquisition is initialization, or RAI, which is quite important if you especially working with object-oriented programming, which is very simple idiom that you should follow if you write object-oriented object-oriented code in C++, which means that a class that you're writing, so each class is responsible for managing its memory. So in this case, you allocate all the resources that you want, the memory and everything, in the constructor of that class. Then you work with your allocated memory in other methods of your class, right? And then it is responsibility of the destructor of that class to free up that memory that you allocated in the constructor. So this is called RAI. So using this principle, you allocate resources in a constructor and release it in the destructor. So the class itself will be responsible for managing the memory. So this is called RAI, and it is one of the most widely used patterns or idioms in C++. Based on this RAI principle, these smart pointers in C++ 11 were implemented. So for example, here, when you use smart pointers, you don't need to worry about the allocations or deallocations. You just can use them and just treat them as normal variables. So you can read this code snippet on your own. But as I mentioned, we don't use a lot these smart pointers in this class. So we try to keep things simple and low level. Okay, any questions about memory management? Let me also check the chat here. Okay. All right. So now let's talk about some of the last structures in C++ and C. So you can, if you want to group some related data, you should use structs. So for example, in this case, we want to have a 3D point, right? And then we have each point in the 3D plane has X, Y, and Z, and they are float. So we can store all of them in this struct data structure in C and in C++. So if you want to combine different types also, you can use a struct. So you can have floats, you can have integers and everything within the same container. And that container is called a struct in C++ and C. So this is the definition. If you want to use it in your program, you can use it like that. So you declare the type of that struct. Then you have a name, and then you can initialize it like that. And when you want to get data from it, so you just need to use this dot notation. So sensor position dot x gives you the x, sensor position dot z, y gives you y, and sensor position dot z gives you z value. Okay, very simple. And finally, we talk a little bit about the functions in C++. So in C and C++, you can have you can pass variables into functions by value and by reference. So I would like to ask someone if you can tell me what's the difference between passing by value and passing by reference in C and C++.
Um, Passing by value, basically, we just pass the actual value. Let's say a pointer x equal 5. I mean, we want to pass 5, we just pass 5. Passing by reference, we pass a pointer. It's the same way when we want to pass an array. We don't pass the whole array. We just pass the address.
Yes, that's correct. So when you so here is the function definition. No, I don't talk about function declaration. This is something that you should be aware of or you can study by yourself. But usually in C and C++, we have header files which contain function declarations and class declarations. And in C++ source file, we have function definition. So this is a function definition, not function declaration. So in this function definition, we have no output, but we have a single parameter input. So when this function is called using this syntax here, right? The value of this input is copied in the function and then is used. So everything is copied here. So this is called pass by value in this case. So if you have a very big object here, very large size and a lot of bytes and kilobytes and megabytes and whatever. So if you pass that object by value, it basically means you're copying everything. So which just slows down your program. But for large objects, instead of passing by values, we pass things by reference, which means instead of copying the whole data into this function scope, we just send it, we just send the address of that data type, right? But if you're using arrays, they are being passed by reference by default. But if you use some other data structures, you have to make sure that if that data structure is big, you send it by reference. So you send the address of that, not the whole data. And the address size in 64-bit systems are 64 bits. So that's quite cheap. Okay. All right, so this is passing by reference and passing by value. You can also define inline functions in C++. So if your function doesn't have a lot of code in it, so it's a short function, you can highlight it with this inline, and the compiler will substitute the definition of this function into your code. So that's also another way of defining functions, but short functions, right? Very small ones. And finally, we have these lambda functions, which were introduced in C++ 11, right? And these are anonymous functions. You can see its definition here. So it's similar to Python's lambda functions. So for example, here we have a lambda function, which is a function without a name. So it doesn't have a reference to outer scope using this notation. It has two parameters, int A and int B, and what it returns is the result of this comparison. Okay, so for example, here we have a sort function that wants to sort this array, this vector, right? And we have this custom lambda function to have this sorting logic. Okay, so lambda functions are used for functional programming, and it's similar to Python's lambda function. So they are anonymous functions, and you can use them as an input argument for your functions. Okay, all right. All right, the last topic for today is I/O in C and C++ to read files and write to files. And these are important because in scientific computing, you usually read data from files. So here in this code snippet, you can see how you can read a file in C++. So for that, you need to import this fstream. Let me clear that again. So you have to import this fstream or file stream. So you have to import this header. And then here you have this type output file stream or OF stream. Then you specify the file name that you want to read, and then you check if the file is open. You just read it using this standard input-output C++ notation, okay? And this is for writing to a file. Sorry, this was writing to the file. And for reading the file, you just need to use this input file stream. You specify the file name, and you check if the file is open. Then you you declare a string here line, and then you using this get line, you read the file line by line. All right. Okay, so I think that's what I wanted to cover about C and C++ syntax. So I would recommend you to take a look at the slides and also try to implement the code that I provided by yourself and check your understanding and see how exactly things work on your computer. Something that I did not cover, but it is very important for you to learn is this CMake, which is an open source build system that manages the build process in C and C++ projects, and that can be used for different platforms. So CMake is very important to build large C and C++ projects, and it is a widely used tool in the industry. So usually in CMake, you have to provide a configuration file like here. So here we just write a project name and some flags for our C++ compiler, and then we specify what we want to create. So in this case, we want to create an executable. If you want to write a library, you just write this add library. So based on this configuration file, you can build your project. And so try to read a little bit about CMake. You can visit their website, cmake.org, and follow their tutorial, and then make sure that you can compile your C and C++ code using CMake instead of directly interacting with the compiler. So that's also very important to know. All right, so I think that's what I wanted to cover. And in the next lecture, we start shared memory programming and we start writing our first parallel application. Okay.